Thank you. So good afternoon, everybody. This is going to be a talk about end-to-end IoT with Dart and Flutter. End-to-end here means two different things. So I'm going to be talking about an end-to-end stack using Dart and Flutter, all the way from a device driver to a Flutter application, and end-to-end encryption from the device to the application, so keeping people's data secure and private. So just a brief introduction for me and my background and kind of why I'm giving this talk. As was already said, I'm an engineer at Atsign. So we're building a platform of personal data stores, and I'll be talking a little bit about how those personal data stores are used with these applications. And as of last Wednesday, I'm a Dart GDE. So I spent last year... Last year, I was spending a lot of time on ARMv7 and ARMv8 support in Dart on Docker, and did a few talks about Dart and full stack Dart development. This year, I'm much more focused on what the performance differences are between AOT and JIT snapshot and some of those things. So I've got an upcoming talk at QCon San Francisco and QCon Plus, which is going to be about that stuff. But my day job is building the platform that's putting people in control of their data. I specifically focus on the scalability, reliability, and operability of the app platform. And that has me spending a lot of time thinking about how we can run, at the moment, tens of thousands of Docker containers with Dart applications within them, and manage all of that and keep it up and stable. Other times I co-host the Tech Debt Burndown podcast. That's me and Nick Selby talking to people about tech debt and how to try and avoid it. Since 2014, I've been a cloud editor at InfoQ, so I write about cloud DevOps and security stuff there. I've been blogging for a long while, and if you want to look up socials, LinkedIn, whatever, then they're all linked from chris.swans.net. So here's the agenda for the talk. I'm going to start off talking through an overview of this demo that we built for Mobile World Congress. So Mobile World Congress was a show in Barcelona, February this year. And the demo that I'm kind of deconstructing here is what we put together for that. We have it downstairs, so I can see a few faces of people who've already been by the Atsign booth and had a close look at the demo. But if after this talk you're kind of like, oh, I'd like to see that and put my finger on it, literally, and see some data flowing, then come by the booth and have a try of it. I'll begin by talking about the Flutter front end. I think that's only fair when we're at a conference that's literally got Flutter in its name. And I'm guessing most of you are kind of into Flutter stuff. And then we'll kind of work our way backwards into the Dart device driver at the other end, and a little on why we ended up having to write a Dart device driver, and why Dart ended up being a pretty good language to write a device driver in. And then bring it all together with the connectivity, security, and privacy elements of that. I'll do a brief detour on the local display. And this is a bit of a, Dart still needs to have some more things for us to be able to easily do stuff that at the moment is better kind of done in other languages. And then a review at the end. My plan is to talk for about 40 minutes on the end-to-end demo. And that should leave us about 10 minutes for Q&A. And then another 10 minutes for people to sort of circulate, grab a coffee, check out things at the stands before the next talks. All right, so an overview of the Mobile World Congress demo. We put together a little video clip, which will hopefully play now. So here is the Raspberry Pi-based demo on a little cake turntable in my kitchen, as we were videoing it for some promotional materials leading up to the show. So what we've got there is a a sensor. This is a MAC 30101 sensor. It reads heart rate and oxygen saturation using an array of LEDs and sensors that are getting the light reflected out of somebody's finger back from those LEDs into the sensors. It's pretty raw stuff, and so we have to do some processing on that in the device driver. But you see on the local display there, it's showing heart rate and oxygen saturation. And then we take that data and we send it into the @sign, which is the personal data store. That @sign can then share that data with an application @sign. In this case, it's for a doctor, Dr. Bob. And the doctor's got full access to the data here. So they're able to see the heart rate and the oxygen saturation. But something we can do with the personal data stores is have control over who has the data and which data is shared with who. So if we choose to, we can share a subset of that data with a fitness instructor, and they're just getting the heart rate data, not the oxygen saturation. So this is something we call differential privacy. And it's an illustration of how using an approach like this puts people in control of the data coming from their things. And we kind of have this saying of your thing, your data, that as we're all getting more and more things in our lives, then we might want to have better control over that. We can apply the same process to biographical data. So the earliest uses of @signs were for sharing things like contact information. And in this case, we're sort of illustrating how a service application could be used to call an engineer and share the contact location so that the engineer is going to show up at the right place. Just briefly talking through the stack that you see there, I mentioned already it's Raspberry Pi based. So if we kind of go from the slices at the bottom, start off with a solid state disk, then the Raspberry Pi itself. Above the Raspberry Pi, we've got a 4G modem. And inside of that modem module, there's also a SIM. We can use that SIM for storing the keys, and I'll explain why that's important later on. And then right at the top, there is the display. And coming off the display, we've got the connection to the sensor. And the sensor is communicating over a protocol called I2C or I2C, which is a very commonly used protocol for attaching sort of low data rate devices. All of the code for this is open source. So as soon as we were done with Mobile World Congress itself, I went home, took the repo that we'd been working on, made sure that there was proper documentation in there, and that's been open source ever since. As we're working on refinements to this, it's all done in public in that open source repo. So everything I'm talking about today, you can go and take a look at the code. And the platform itself is also open source, so you'll find all of the platform code in the same open source organization. And so pretty much every aspect of what we're doing here is entirely open for you to kind of look over our shoulders and see what we're doing. And if you see things that you think need improvement, then please raise issues, do pull requests. We're really happy to get that stuff. So FlutterVikings, you're probably interested in the Flutter front end. The first thing that a user is going to see is this sign-in. This particular screenshot comes from a Windows desktop. One of the beauties of using Flutter is that we can have a common code base across different types of mobile device and also different desktop applications. In this case, I've already kind of associated it with my @sign. So my @sign is CP Swan. And it's sort of already there for me to press the go button. But if I didn't already have an @sign, I could have just pressed the set up a new @sign button there. And that would take me through the provisioning and onboarding process for an @sign. And when we do that, what's happening behind the scenes is we're taking people through a chooser application. Free @signs are available, and they're kind of automatically generated. So we let people pick an automatically generated one that they like the look of. There's also the option to buy @signs for very specific names. So CP Swan is the name I use for all the socials. So when I joined the company, I ended up buying that @sign. And an @sign comes with a key pair. So that's something that gets created as the @sign itself is created. And to give people the chance to reuse their @signs across different applications, they're able to export that key pair so it can be reused later on. Once somebody's signed into the application with their @sign, they're then taken into this main screen. So you saw a snippet of this during the video. And all that we're doing here is using a couple of gauge widgets to present the data to the person using this application. So in this case, we're taking 2 data sets, one for heart rate and one for oxygen saturation, and just presenting those on gauges. More generally, what we're doing as a platform company is building a suite of Flutter widgets that's going to be useful to developers building on top of the platform. So some of that is around the onboarding, but beyond that, we're kind of getting into things like gauges to help people with the UI aspects of the applications that they're building. As we focus more on IoT, then there's more and more where we're looking at what kind of applications are people building to help manage the things, and what are the elements of those applications that are reused again and again, and how can we help people do that as quickly as possible by having as many components already available. So beauty of Flutter is it's the same application for Android. And we're quite often building continuous delivery pipelines for these applications so that we can automatically crank them out and have them to be Play Store and App Store and Windows Store ready in order to then kind of tap into the distribution pipelines for those apps. And of course, iOS as well. 2 screenshots here. So the one on the left is an iPad in landscape orientation. The one on the right is an iPhone. And I think that's just illustrative of the fact that Flutter provides a really flexible environment for developing this class of applications. So I've started with the user experience on the handset, and I'm now going to kind of go all the way to the other end of the end-to-end with the Dart device driver. So as we were going to Mobile World Congress, we were going there with a partner called Zariat. Zariat is a connectivity provider for IoT, and they're very much focused on security. So I was talking to the head of security at Zariat about this demo and what kind of thing would have an impact. And he said, I've seen some YouTube videos of applications that have been made with these heart rate and oxygen saturation sensors. And I went and looked at those and seemed pretty good. People were building apps with Raspberry Pis and Arduinos and that kind of thing. I went and looked on Amazon, and this Max 3100 sensor was there for about £4, I think. So very cheap and easy to get hold of. On the right-hand side, it kind of gives an illustration of how this works. So it's got a couple of LEDs in it. One's visible, the other one's infrared. It shines those LEDs into your finger, and then it's measuring what's reflected back. And from those measurements, you can then compute the heart rate, which comes from the movement of blood past the sensor, and the oxygen saturation, which comes from the amount of absorption differential between infrared and visible light. And that can be calculated with a different algorithm. So all of this seemed pretty straightforward. And that led me into what I kind of label the programmer's lament here. We do these things not because they are easy, but because we thought they were going to be easy. So when it came to me actually sitting down and coding this stuff, it turned out that all of the Raspberry Pi demos had been faked. So the Raspberry Pi driver for that particular device, it's a Python driver, and all it actually provides to the Raspberry Pi is raw readings of the infrared and visible light LED reflectance. And so from those raw readings, you can calculate the heart rate and the oxygen saturation. But that's the kind of thing that people expect the driver to do for them. And that driver doesn't do that. So we went looking around for something else. And we found there's newer versions of this sensor. And so as I was first looking, all of the stuff I found online said the Max 30105 was the latest and greatest. And I went and ordered one of those. And one of these came in the post, a 30101. And I'm like, well, that's got 4 less. So it must be older and not as good. And actually, I sent the first one back. And they sent me another. And it was another 30101. And at this point, I'm kind of like, what's going on? I thought I was getting bad old inventory. And in fact, that is the latest device. And the drivers for it are a little bit newer, but still don't actually work properly with the Raspberry Pi. So the driver that comes with that device can do heart rate, but it can't actually do the oxygen saturation. And since we wanted to show off differential frequency, we actually wanted both pieces of data. So what we ended up doing is taking the Arduino driver, which is a C++ driver, and our favorite bits of the Python driver, and we ported that to Dart. So you can go into PubDev, and you can search for Max 30101, and it will pop up this driver. The good bit for us is we didn't have to write everything from the ground up. So this driver itself is a pretty low-level piece of code that's able to take readings off the I2C bus and turn them into heart rate and oxygen saturation readings that we can then send into the rest of the pipeline. But we didn't have to actually write the I2C stuff. There was a PubDev package already there that did that for us. So we weren't having to kind of reinvent the whole world to make it work. So we stand on the shoulders of giants. There's a package there called Dart Periphery. That takes care of I2C. And at a low level, when you plug one of these into a Raspberry Pi, there's some I2C command line utilities, and you can just see that it's connected. You can see the address that it's connected on. That address is hard-coded into the device itself. And so we were able to then just put that address into the package that we were building to read out of that. We were fortunate as well that the C++ code is exceptionally well documented. The code itself is pretty good idiomatic C, but there was a blog post explaining every aspect of it, and really in detail explaining how the device works, things that we would get from the data sheet to describe how the various readings are actually related to physical things going on in somebody's finger, and how that can be turned into readings that would then be sent into the application. OK, so moving on to how do we get stuff from the device into the application? Well, to do that, we need connectivity. And as soon as we create connectivity, then we're creating concerns for ourselves around security and privacy. So there's lots of ways we could get the data from the device into an application that would just provide the connectivity. We could send stuff through a plain HTTP API or something like that. But that would bring with it concerns over how secure is that data and how private is that data. And that's really why we end up using our platform. So busy slide warning, lots going on here, and I'll take a bit of time to sort of step through what's happening. So if we start at the left-hand side, we've got our IoT device. And so it's got the connectivity to the sensor. It's getting readings off the sensor. Our Dart device driver can turn those into data that we want to make sense of later on. So that's the application that's sat on the device, the driver up to sending some sensor data. So we want it to get to the right-hand side, and that's the receiving application. And that's the application that's written in Flutter, and it's just the simple gauges. So that's picking some data out of a personal data store and presenting it in a way that's sort of clear and understandable to the person using that application. But to create the end-to-end channel, we need some intermediate elements here. And also, we need to manage some keys. So end-to-end encryption depends upon keys. And we're just using regular key pairs here. Everything that's on show downstairs is using RSA key pairs. We've been working on a couple of the elliptic curves. So there's an elliptic curve used for IoT safe. And there's a different elliptic curve that's becoming quite popular now for SSH. Both of those are in play for sort of future applications. But even just with RSA keys, we need to do some key exchange. So the sender needs to have the receiver's public key, and the receiver, in turn, needs to have the sender's public key so that they can each send and receive encrypted messages from each other. And so this is where the caches come into place. And a concept in our platform is this idea of a secondary server. So the personal data store is realized in a place on the internet that we call a secondary server. We run this as a hosted platform, but we also offer people the option of self-hosting. So that means that it can be run on a Raspberry Pi or an Amazon EC2 instance or a virtual private server or a PC under somebody's desktop. We don't actually care. And we've spent a lot of effort making sure that that is a user's choice over where they put stuff. So the flow of data then is on the device. The device wants to send data to an application. So the device reaches out to its secondary server and says, I've got some data for this @sign. Its secondary server looks up that @sign. That's what the root server is for. The root's like a naming service. And it will provide the address and port of the @sign, the personal data store that we want to talk to. The secondary server of the device is then able to say, OK, give me the keys for the receiver. And it'll reach out to the receiver's secondary server, ask for its public key, and provide that back down the chain. The device has now got the public key of the receiver. And so it can start encrypting things that are going to be received end-to-end encrypted. And the same works in reverse. So the receiver is able to fetch the public key of the sender. And with that key in hand, it can do end-to-end acknowledgements that it's received the data. But it can also ensure that it's getting data from an authentic source. So at the bottom of this illustration, you see the two sort of component classes. So the root server is the naming service that lets us find the personal data stores. And then the secondary servers is the array of the personal data stores themselves. We've got tens of thousands of those on the platform at the moment under our management. A small percentage of those are not under our management, and so they're the self-hosted versions. And as we're working with device manufacturers, we're kind of getting a mix of people that want to host in their own data centers or on their own cloud platforms, people that want to just use our managed service to do all of that for them. So where do the keys go? End-to-end encryption depends upon keys, and keys need to be securely stored and managed. That's pretty easy on phones. So all of the devices we've got in our pockets have actually got components inside of them that are there specifically for the purpose of securely managing keys. So you've probably heard of this idea of a secure enclave. Flutter provides a whole bunch of APIs to do things with the secure enclave. And we can use that to generate keys inside of the secure enclave and then export them. Devices generally do not have secure enclaves built into them. So they're using different class of system on chip generally. If you take something like a Raspberry Pi, the system on chip in a Raspberry Pi is designed for a set-top box. The set-top box people didn't need secure enclaves for key management, and so they didn't put them there. That leaves us looking for another place to secure the keys. And the place that we found in this case is the SIM card. So SIM stands for a subscriber identity module. That identity is a cryptographic key. And so SIMs are essentially designed for storing cryptographic keys. And we can put other cryptographic keys in there as well as the cryptographic key, which is the IMSI, which is associated with a phone number. And the reason for doing that is to keep down the cost of the bill of materials. So for sure, we could add a TPM, a trusted platform module, to a device in order to store keys. But that's another sort of $1.50 for the TPM itself. And then any additional device that you add to a thing is growing the size of the printed circuit board. It's growing the complexity of the manufacturer. It's introducing more potential supply chain issues. And so people don't want to do that. So if there's going to be a SIM card there anyway for connectivity, why not just reuse it in order to use it for key management as well? So SIM isn't the only option. Any kind of connectivity will do here. So with the Raspberry Pi, we've got three choices. We've got wired with the Ethernet port. We've got Wi-Fi with the embedded Wi-Fi. And we've got cellular, which we've achieved by putting the cellular hat onto it. And with the demo app, we can actually use any of those for the connectivity. But we're still storing the keys in the SIM. Another aspect of what we've been building here is for admin access. So I've kind of talked through the flow of data from the device to an application from the user's perspective. But very often, the manufacturers of the device need to get admin access, or even the user of the device might want to be able to configure or reconfigure things. And this is done so that things like firmware can be upgraded, so that maintenance tasks can be carried out, and that sort of thing. The traditional way of doing this has meant leaving some kind of admin port open on the device. And that causes a whole bunch of problems. So if you're leaving a port open, that's generally a problem from a security perspective, but it also makes things tricky for networking. If you're leaving a port open, then you've got to be able to find that port and connect to that port. And often from networking, that means you've got to have static IPs and that sort of thing. And all of that ends up being more cost and complexity. So what we can do with the app protocol here is use it as a management plane for initiating SSH connections. And we've packaged that up into an application we call SSH no ports. So this is another one of our GitHub repos. And what SSH no ports does is allows people to make an admin connection to their devices without any ports being open at all on the device. So not even port 22 for SSH itself. And what it's basically doing here is using the app protocol and the associated @signs as a management plane that initializes an outbound SSH connection. And then that outbound SSH connection can be connected up with an SSH client. We can throw ngrok in there as a way of ensuring that the tunnels connect. And that means that both ends can be behind NAT and all of the firewalls and anything else that people might have in place. So quite often when I've been talking to people about using Dart and Flutter and end-to-end encryption, they kind of go, oh yeah, it's kind of obvious why people would want that for medical devices, more concern about privacy and whatever else. And then when I mentioned this admin access thing, they're like, oh, everybody wants that. Because it doesn't matter what category of device it is, there's generally a need for admin access, and the network arrangements and security concerns about it has been a sort of thorn in the side of all device manufacturers. So lastly, the local display, and this is at the moment the bit we didn't use Dart for, and it's just worth kind of touching upon it and mentioning why. So the device itself is called a PyTFT hat. These are kind of designed and built by a company called Adafruit Industries. They do a whole range of sort of popular add-ons for Raspberry Pis and Arduinos and other kind of maker development environments. And it presents itself to the Raspberry Pi and Linux running on the Raspberry Pi as a frame buffer device. Now, this is pretty normal, but the challenge here is how do we write into a frame buffer device? We could just let the Raspberry Pi mirror its X windows into the frame buffer device, but that quickly gets awkward and means it's difficult to separate the console display from what's happening on the display at the top of the stack. And we wanted to have those separate. So it turns out the easy way of driving a frame buffer device is with a framework for Python called Pygame. Gaming and frame buffers go together pretty well. And we can get the data into Pygame using a popular IoT protocol called MQTT. And so what we actually do here is we put the raw data onto an MQTT bus and then read it off into the local display and also into the Dart sender application that's putting it into the personal data store. So Flutter is more than capable of driving frame buffer devices. There's lots of great display work already being done in Flutter, but the pieces weren't quite there for us to put them together in terms of being able to easily draw Flutter stuff on such a low-level frame buffer device on the Raspberry Pi. So that was where we shaved off a bit of time by just using existing stuff with Pygame. Okay, so this brings us to the review. I've talked about the sort of reason we did this in the first place and an overview of what we put together. So a Raspberry Pi-based demo for Mobile World Congress in order to show off end-to-end encryption. And along the way, we built something that was end-to-end Dart. The Flutter front end makes use of our widgets in order to display data coming out of a personal data store. And the Dart device driver backend was a low-level implementation of the sensor driver so that we could capture the heart rate and the oxygen saturation in the way we wanted to in order to send them into the rest of the Dart stack. For us, the important bit is the connectivity, security, and privacy, and that's making use of our platform in order to accomplish the end-to-end encryption. And the key is the keys. So having key management being done in the right places was essential. And that's easy in the mobile environment, but we've been making use of the SIM card to do that in the IoT environment. And then lastly, the local display was the leftover bit that we found wasn't easy to do with Dart and Flutter. And for that, we used Pygame. So I stole this slide from my colleague, Anthony. So go and see his talk tomorrow about Flutter DevRel. But Takshal Duha, I hope I've said that properly.